Our first speaker is Jendrik Seipp, and he's going to tell us about a comparison of cost partitioning algorithms for optimal classical planning.
Thank you. So, this is joint work with Thomas Keller and Malte Helmert. And the setting that we're investigating here is optimal classical planning. And we use for this setting a star search plus an admissible heuristic. And in this work, we focus on abstraction heuristics. So to get us all up to speed, what are these? Well, this is an example planning task, a concrete task where we have states and operators, like the black one, the blue one, and red and green one. And they have different costs. So these two cost 4, these two cost 1. This will be important later on. And we have a goal state. This is S5 in this example. And here we see an example abstraction where we combine, for example, S1 and S2 into a single abstract state. And then this means that this operator becomes a self-loop in the abstraction. Okay, so what's the problem with using abstraction heuristics? Well, usually one heuristic is unable to capture enough information to solve the problem. That's why we want to use multiple heuristics. But then the problem becomes, how do we combine these heuristics in a way that is still admissible, because we want to guarantee optimality. So one way of doing so, if we have these two abstractions, the one we saw earlier and a new one, is computing the separate estimates for S1, which are 5, both 5 in this case, and then use the maximum over these two heuristics, which is still admissible because each individual heuristic is admissible. But this only selects the best heuristic in each state and doesn't really combine the information. What does combine the information is cost partitioning. And cost partitioning works by splitting each operator's cost among the heuristics, and in a way that the total costs don't exceed the original operator costs. And this is essentially combines the heuristics and allows summing over the heuristic values admissibly. So the question becomes, how do we come up with these cost partitionings? And there are several algorithms in the literature, and in this work we compare these both theoretically and experimentally. And first I would like to give you an overview of what the algorithms are, and then I'll go into the theoretical and experimental analysis. So let's start with optimal cost partitioning. And the optimal cost partitioning is the one with the highest heuristic value for a given state among all cost partitionings. And it has been shown that this is computable in polynomial time for abstractions, but it is too expensive usually to compute for even small abstractions in practice. So what would we get from optimal cost partitioning in this example? Well, it would recognize that it makes sense to use a cost of 4 for the black operator here, and use the cost of 1 for the blue one, and so on. And then we would get an estimate of 5 plus 3 for the two abstractions, yielding the optimal heuristic value of 8. So now that we know that this is not really feasible to compute in practice, there are several alternatives that are actually computable. So one of these is post-hoc optimization, and it's related to optimal cost partitioning closely because it also solves, it also can be computed with a linear program. And what it does is it computes the best factor W between 0 and 1 for each heuristic in such a way that for each operator the sum of the relevant heuristic factors is smaller than or equal to 1. So in this example we see that, for example, for the black operator it is relevant both in the first and in the second heuristic. So the factors for the two heuristics have to be smaller than or equal to 1. Similarly, for the red operator, it's only relevant in the second abstraction. Yeah? So it only incurs this constraint. And then we use the costs W times the original cost if the operator is relevant for H, otherwise we just use 0 costs. What does it mean for this abstraction, or for the two abstractions? Well, we have seen that this is the tightest constraint, so we have to ensure that the two weights sum to at most 1, and we can use any partition of 1. So we chose 0.25 for the example for the first heuristic and 0.75 for the second one, which induces these transition weights. And in summary, we get a heuristic value of 1.25 for the first abstraction and a heuristic value of 3.75 for the second one. And in total, we get a heuristic estimate of 5. What else do we have? So we have greedy 0-1 cost partitioning. And this algorithm works as follows. It orders the heuristics. So for example, choosing to order heuristic 1 first and then focusing on heuristic 2. And then it uses the full cost for each operator for the first relevant heuristic. So in this case, all these 3 operators here are relevant in this abstraction. So they get their full costs. And this one is not relevant, so we keep the costs and we can use it here. But all the others are already 0, so we get a heuristic estimate of 5 plus 0 for this abstraction. But we can already see a problem here. So here we used costs of 4, but this didn't help us anything because we essentially wasted the cost of 3 here. And this is what the underlying idea of saturated cost partitioning is all about. Because similarly to the previous cost partitioning algorithm, we order the heuristics, but then for each heuristic, we use the minimum costs that preserve all heuristic estimates for this heuristic. And then we can use the remaining costs for subsequent heuristics. So in this example, we would only use costs of 1 here and store the others or save the other costs for the other abstraction, yielding an abstraction as a heuristic estimate of 5 plus 3 equaling 8. Okay, what else do we have? We have uniform cost partitioning, and it only just distributes costs uniformly among the relevant heuristics. How does this work? Well, we just divide, since we have 2 abstractions where this operator is relevant, we divide the operator costs by 2 and do this for the relevant heuristics. So here, this operator is not relevant, so we can use the full costs in the second abstraction, yielding an estimate of 3 plus 3 equaling 6. But again, we see that we waste costs here. So we don't actually need to use a cost of 2 here because there's a cheaper path going over the green arrow. And this is what we saw, and similarly to saturated cost partitioning, we came up with a new version of uniform cost partitioning, which we call opportunistic uniform cost partitioning. And it combines essentially saturated cost partitioning and uniform cost partitioning by also ordering the heuristics, and then similarly to uniform cost partitioning, distributing the costs uniformly among the heuristics. And then, but only using the saturated costs for H, so only the costs that are actually needed in this abstraction, and then we again use the remaining costs for subsequent heuristics. So in this case, we would offer the heuristic costs of 2, but it would see that it only needs 1, and then we can use the 1 in the subsequent abstraction. And yeah, giving us a heuristic estimate of 3 plus 4 equaling 7. Okay, the last algorithm that I want to present is the canonical heuristic. And it computes the independent heuristic subsets. So the subsets where each heuristic does not use an operator twice, or is, for which no operator is relevant twice. And then it computes the maximum over the sums. And we already saw in this example here that there is an operator that, or there are 2 operators that are relevant in both abstractions. So the independent subsets are just singleton subsets of the first and the second heuristic, which means we maximize over the individual estimates, giving us an estimate of 5. Okay, so now the question is, how do these algorithms compare? And we start with a theoretical analysis. And prior to our work, we only knew a result from Pomerening at RDE, who showed that the post-hoc optimization heuristic dominates the canonical heuristic. And in our work, we proved 3 new results showing that the saturated cost partitioning dominates our new dominates the greedy 0-1 cost partitioning heuristic, and also we showed that this heuristic dominates, for at least one order of heuristics, the canonical heuristic. Also we showed that our new heuristic, the opportunistic uniform cost partitioning, dominates uniform cost partitioning. And we also showed that the 3 heuristics on the left are incomparable. So for each of these pairs, there is an example where one algorithm performs better, and there's an example where the other performs better. This leads us to our empirical comparison of the algorithms. And in our paper, we used 4 different test beds for the analysis. And we analyzed our algorithms on hill climbing pattern databases, systematic pattern databases, Cartesian abstractions, and landmark heuristics. And in a related paper, we showed that for the algorithms that depend on the heuristic order, it's usually preferable to use multiple orders. So for these algorithms, we evaluate not only a single order, but also a set of diverse orders. Okay, so let's have a look. We only focus on the systematic PDBs in this talk, because otherwise there would be too many results. So in this table, what we see is a comparison on a domain-wise basis between the cost partitioning algorithms. So for example, this comparison here between 14 and 0 tells us that opportunistic uniform cost partitioning solves more tasks than uniform cost partitioning in 14 domains, while the opposite is true in 0 domains. So for this analysis here, let us keep on the diagonal, which means that we also always compare the previous to the current to the previous cost partitioning algorithm. So we see that this one is better than this one, but once we use multiple orders for opportunistic uniform cost partitioning, it doesn't really help us much. So the scores are 8 to 9, so using multiple orders here doesn't help us much. The next comparison, we see that greedy 0-1 cost partitioning is much worse than opportunistic uniform cost partitioning and uniform cost partitioning, so 4 to 22. But interestingly, once we use multiple of orders for greedy 0-1 cost partitioning, we get much better, and actually outperforming all the previous 4 algorithms. Even better is to use saturated cost partitioning in this setting, which outperforms greedy 0-1 cost partitioning in 16 domains, while the opposite is true in only 9 domains. And even better is to use multiple diverse saturated cost partitioning algorithms, orders, and this outperforms all the previous algorithms. Okay. The compared canonical heuristic and the post-hoc optimization heuristic is not comparable to this performance. We see that, for example, the canonical heuristic is better than the saturated cost partitioning in 8 domains, while the opposite is true in 23 domains. Similar picture we have for post-hoc optimization. And we see that optimal cost partitioning is usually the worst choice coverage-wise, because it's just too slow to compute. Okay, we can see why this is the case, because the saturated cost partitioning heuristics are just way more informed than the post hoc optimization. So these are the expansions, excluding the last F layer, and we see that we usually use several orders of magnitude less expansions with the saturated cost partitioning heuristic. So summing up our results that we saw in all settings, it is preferable to reuse unused costs, assign them greedily, and use multiple orders. And this is essentially what saturated cost partitioning does. So this raises the question of how this fares against the current state of the art. And we compare our best performing algorithms from each setting against Simba, which won the last IPC. And we reran all algorithms using H2 mutexes for a fair comparison. So we can see that all these saturated cost partitioning algorithms using different heuristics, there are cases where one or the other is better, but usually the Cartesian abstractions perform best. Landmark heuristics are not as strong as the other heuristics, and there's not a clear picture against the state of the art, at least not on the domain basis. So Simba is better than the hill climbing PDBs, the systematic PDBs, and the landmark heuristics. But the Cartesian, it's a close call. But on a total coverage score, the Cartesian heuristics solve a little more problems. So there's related work that was actually presented earlier at SOX, where we actually combine these three types of abstraction heuristics, and we came up with a better method for finding good heuristic orders, and this actually raised coverage significantly. So to sum up, we showed new dominance relations between cost partitioning algorithms. We actually came up with a new cost partitioning algorithm and showed that saturated cost partitioning is usually preferable in all tested settings. Thank you.
Questions? I have one. So back in the landmark page, right, we had the action landmark optimization, right, where if we detected that an action is an action landmark, then we assigned it the full cost and we divided the others uniformly. Mm-hmm. So is that a special case of the opportunistic uniform?
I think so, yeah.
What questions?
It seems that it's very important to have like a diverse cost partitioning, right? In partitioning. Have you thought of trying to use at the same time diverse saturated cost partitioning, but also the uniform opportunistic cost partitioning? So combine multiple methods, cost partitionings at the same time?
That's an interesting idea, but we haven't tried it. So, in our tested settings, it was surprising that even a single saturated cost partitioning order was better than all the other algorithms, even when they used multiple orders.
Any more questions? So let's thank the speaker again.